Okay, welcome everybody to a special session of the Graphs and Matroids workshop. And today we're seminar. And today we're going to have a talk by James Oxley, who's going to tell us about the legacy of Dominic Welsh. And I'm very pleased to see that we have several members of the Welsh family here. So welcome to them. And James, I'll pass it over to you.
Thanks, Jim. Well, to summarise Dominic's legacy, he was an exceptional mathematician, an inspirational teacher and writer, and an extraordinarily kind and generous man with whom doing mathematics was challenging but joyous. Move forward. How do I move forward on mine? I was able to move forward before, Zach. How can I do that?
Maybe just click on the slides and then try.
Okay.
Yeah, or just click anywhere on the page.
Good.
Yeah.
Thank you. Okay, so much for practicing. Okay, so this is one of a number of pictures that I took or were taken with my camera. This is Dominic in the mid-1980s in the South Lodge, and you'll see in the corner of the picture Rubik's Cube, which was ubiquitous at that time. The sources that I used for this talk, there's a wonderful obituary written by one of Dominic's students, Geoffrey Grimmett. That's to appear in the Bulletin of the London Maths Society soon. Graham Farr did a very thorough historical treatment of Dominic's legacy, and in particular his work with students. Dylan Mayhew and I contributed to this a little bit, but most of the work there was done by Graham. Peter Cameron was Dominic's colleague at Merton College in Oxford. Peter was the pure mathematics tutor. Dominic was the applied mathematics tutor. They were colleagues for 11 years. And Peter has got some reflections there about Dominic. And then there was a tribute to Dominic posted just after he died by his family. And that's got a bunch of lovely material. So I recommend all of those sources to you. Dominic's collaborators. So just to give you an idea of his stature as a mathematician, let's start with the letter A. Oh, Noga Alon. Let's go to the letter L, Lotzi Lovas. What about the letter S? Paul Seymour, Richard Stanley. Any time you've got a group of mathematicians of that stature working with you, it's telling you something about your status in the profession. David Wood, who's one of Dominic's students, one of Graham Farr's students, maintains the academic family tree of Dominic, and that's extensive. Dominic's first student was Adrian Bondi, and he wrote, Dominic was always bubbling over with ideas. His enthusiasm was contagious. And that's absolutely true. 28 of us were lucky enough to be his doctoral students. I'm going to use the Oxford abbreviation DPhil. Everywhere else in the world would be PhD. 28 DPhil students, another 3 students Dominic was the joint supervisor of. What sort of impact did Dominic have? Well, 2 of his students, Peter Donnelly and Geoffrey Grimmett, are now Fellows of the Royal Society. And Dominic did a lot of teaching of undergraduates, very gifted undergraduates, including these 3 men. Andrew Wiles, you'll know he settled Fermat's last theorem. Peter Kronheimer is a professor at Harvard. Dominic Joyce is a professor in Oxford. Between these 3 men, they've won over 20 major mathematical prizes. This is some legacy. You might like to try and identify this. This was in 1986 in Marseille. 4 of us solving problems. I'll leave it till later for you to try to identify them. Dominic's early life. Well, he was born August the 29th in 1938 in Port Talbot, Wales. Both of his parents, James and Teresa, were teachers. He had a younger brother, David, 2 years younger. He became a professor of classics at the University of Ottawa. And now we start to see a bit of a pattern. And then the pattern is confirmed when we see that Dominic's 2 younger sisters, Mary and Teresa, both became teachers. Dominic's education. Well, he went to St David's School in Swansea first. And at that school, his father was the headmaster. And then he went to Bishop Gore Grammar School in Swansea. And from there, he went in 1957 to Merton College, Oxford. At that time, J.R.R. Tolkien, of Lord of the Rings fame, was Professor of English Language and Literature. He was the first student ever from his school to attend Oxford. He also was offered a position at Cambridge. He completed his bachelor's degree in 1960 and then went for a year on a Fulbright to Carnegie Mellon University and also to Bell Labs. More about Bell Labs later. Dominic loved sports and games, and he was very good at them. In particular, he was an excellent schoolboy rugby player. He almost tried out for the under-18 Wales team. But if you knew him at all, he would have told you that he was born on the 29th of August and the cutoff for being eligible was September the 1st. So he didn't make it. But he did play for Merton College, and he did play on the Oxford second team, and he did fracture his skull. Very few of you, I've discovered, will know the names of the next person that I mentioned, but he played on the the Merton College team with Chris Christopherson, a movie star, a country singer, and a Rhodes Scholar. You don't often hear Rhodes Scholar and country singer in the same sentence. Lots of us played games with Dominic. Speed chess, pool, croquet, tennis, real tennis, table tennis. Now, table tennis was a particular challenge if you played in the basement of Dominic's house because the table was flush up, the side of the table was flush up against a wall. And it took you a while to recognize that Dominic's main shot was to hit it close to that wall so that you couldn't return it. This is a picture taken from Dominic's tribute site of Dominic on the river with a Merton crew. You can see Dominic in the 3rd position there. Dominic returned from the US and did his doctorate in Merton. It was with John Hammersley, subsequently became a Fellow of the Royal Society. Now, you all know Dominic's work in combinatorics. You probably didn't know, many of you, that his PhD thesis, his doctoral thesis, was in probability theory, topics in stochastic processes. And Geoffrey Grimmett, sorry, I'll get to that in a minute. 1966, he became a Fellow of Merton. 1992, he became a personal chair. And then at that time, you were mandated to retire from Oxford when you reached the age of 67. So Dominic retired and we had a retirement conference for him in Oxford. His doctoral research was on percolation. Now, when Dominic explained percolation to me, he said, take the unit grid in the plane and assume that you've got a water source at the origin. And now each edge of this grid is open with probability P or closed with probability 1 minus P. And the question is, what's the value of P so that the set of wet vertices becomes infinite? Now that's a very quick summary of percolation, which was Dominic's first area of research. But I mentioned Geoffrey Grimmett's name a few moments ago. So Grimmett is a fellow of the Royal Society. He was professor of mathematical statistics at Cambridge until he retired. He's written about this work that Dominic did with Hammersley had an enormous influence over the intervening 60 years on the theory of random spatial growth. One of the features of Dominic's work was that he was never content with just staying in one narrow area. He was always trying to learn new things. And there are really three distinct features that you can, distinct stages in Dominic's career. There was percolation, then Matroid theory, and then it's hard to decide which came next, but the polynomial and complexity theory. What was it about Matroid theory that interested Dominic? Well, he was introduced to the subject at a seminar by Nash Williams, a most stimulating seminar on the applications of Matroid. What was it that Nash Williams did? Well, he'd introduced the operation of Matroid union. Now, those of you who know Matroids will know what this operation is. You take two Matroids on the same set, their union has the same set as ground set, and the independent sets are independent set in the first Matroid, union and independent set in the second Matroid. What's the big deal about this? Well, you can get a nice formula for the rank function. You want to get the rank of a set X in this union. You look over all subsets Y of X, rank of Y in the first Matroid, rank of Y in the second Matroid, add X minus Y, and then minimize. So why is this formula good? Well, what it does for you is that it gives you really quick proofs of graph results of Tutt and Nash-Williams and of Matroid analogues of these results due to Edmonds. What do these results do? Well, the results of Edmonds gave necessary and sufficient conditions to have k disjoint bases in a matroid. If you like, k edge disjoint spanning trees in a connected graph. Also, to have m independent sets covering the ground set of a matroid. In the graph case, m forests that cover the edge trees, the edge set of the graph. So these are quick and beautiful results. And that was when Dominic was asked about what was it about mathematics that he loved so much. He talked about the search for beautiful patterns. In 1983 to 1987, Dominic was the chair of the British Combinatorial Committee. Dominic had a very well-developed sense of duty, and there was never a job that he failed to do, even some really horrible jobs, which he's acknowledged, including being chair of the Mathematical Institute in Oxford, which he did for 5 years. But this was a more pleasant job, being British Combinatorial Committee chair. In 1985, that conference, the British Combinatorial Conference, was held in Glasgow. This is the Glasgow City Chambers. You can see it's a very imposing building. And the Lord Provost of Glasgow held a banquet for us who were at this conference. And you can see it's a magnificent building that was the banqueting hall. Really beautiful. And Dominic was mindful of his audience, and he talked about what it was that he liked about mathematics, and it was the search for beauty. Many of you will know G.H. Hardy, the Cambridge mathematician from the middle of the 1900s, wrote eloquently about beauty and mathematics. In particular, he wrote, "Beauty is the first test. There is no permanent place in the world for ugly mathematics." Matroids versus graphs. This is a title of a 1968 conference paper that Dominic wrote with Frank Harari. The purpose of this paper was to help graph theorists to appreciate the important link between graph theory and matroids. Now, those of you at Waterloo might find that this echoes one of the sentiments of one of your great contributors, Bill Tutt. And in fact, it was Tutt who wrote the Maths Review's entry for Dominic's 1976 book, Matroid Theory. Here's what he wrote. "It's been said that to get a theorem on matroids, we should take a known one on graphs, rewrite it and its proof so as to make no mention of vertices, and then replace the word graph with matroid. Chapter 5 goes far to justify this recipe." So what was chapter 5, you ask? Well, chapter 5 is about Tutt's work. In 1961, Tutt had a theorem called the Wheels theorem. He generalized that in 1966 to matroids, the Wheels and Whirls theorem. What is this theorem? Take a three-connected simple graph, and what you'd like to do is contract an edge or delete an edge so that you can be three-connected and simple. You can always do that unless you've got a wheel. Or in the matroid case, you can always do that unless you've got a wheel or a whirl, and a whirl is a matroid closely related to a wheel. What about Dominic's early matroid research? Well, one early paper that I particularly like is called Euler and Bipartite Matroids. If you take an Eulerian graph and it's planar, and you take the dual graph of that, that will be bipartite. And that result was generalized by Dominic to binary matroids. If every circuit in a matroid has even cardinality, if and only if the ground set has a collection of disjoint co-circuits whose that union to the ground set. Dominic did quite a bit of work in transversal matroids, papers in these 4 years. There were two schools in Britain working in matroids at that time. Dominic and Aubrey Ingleton in Oxford, and then in Sheffield, there was Leon Mirsky, Hazel Perfect, John Pym, and then Dominic's student Mike Piff went there as well. I want to state one of the results there. If you combine Dominic had a student named Joan D'Souza. They wrote a paper together in 1972. Adrian Bondi was Dominic's first student. And then Michel Lasvernius was a French mathematician who made lots of really important contributions to matroids starting in the 60s and going to the early 2000s. You've got a class of matroids, transversal matroids. You've got another class of matroids, graphic matroids. What if you say, I want to know what the graphic and transversal matroids are? Well, they turn out to be the matroids which are binary and transversal, and they can be characterized by this excluded series minor condition. There are no series minor isomorphic to the 4-point line, to the cycle matroid of K4, or to the doubled cycle of length K. And if you don't remember what a series minor is, it just means you're allowed to do any deletion that you like, but the only contractions you can do amount to, in the graph case, shrinking a path, in the matroid case, shrinking a co-circuit of size 2 down to a single element. Dominic was always asking questions, and in particular, he was very good at the end of seminars of pinning down speakers as to exactly what they meant. Never in a hostile way, always with a lot of humour. And Steve Noble wrote in the obituary that Jeff Grimmett has penned the following: I've never come across anyone who could do whatever it was Dominic did to make the discussion so lively and informative. In 1969, there was an Oxford conference called Combinatorial Mathematics and its Applications. Dominic organised this conference, and this conference is now viewed as the first British combinatorial conference. Dominic also organised what is the third British combinatorial conference. This year, in July, there'll be the 30th British Combinatorial Conference at Queen Mary, University of London. Now, there are a lot of really nice problems in the paper that Dominic wrote for the proceedings called Combinatorial Problems in Matroid Theory. The ones that I want to talk about are enumerative, and some of you will anticipate why that is. Sequence of numbers is unimodal if it goes up, stays steady for a while, and then goes down. I'm sure you're all familiar with this. A somewhat stronger condition is that if you take any number in the sequence and you square it, that's greater than or equal to the product of the number before and the number afterwards. So let's look at the number of k element independent sets in a matroid as k ranges from 0 to the rank of the matroid. Problem P13 in Dominic's 1969 paper was that this sequence was unimodal. And that conjecture was strengthened in 1972 by John Mason. Not only is this sequence unimodal, but it's actually log concave. Now I'm going to take what appears to be a diversion that has nothing to do with this. I'm going to start talking about the characteristic polynomial of a matroid. Some of you will recognize this as an evaluation of the Tut polynomial of the matroid. It's actually a generalization also of the chromatic polynomial of a graph. So if you have the characteristic polynomial of a matroid, Dominic would have called it the chromatic polynomial of the matroid. And you multiply that by lambda to the number of connected components, then you get the chromatic polynomial of the graph. So if you've never seen this before, think of it as a generalization of the chromatic polynomial of a graph. Rota looked at this polynomial, and in 1964, he showed that the coefficients of it alternate in sign. So here we've got the chromatic polynomial, the characteristic polynomial of a matroid. The coefficients alternate in sign. In Dominic's book in 1976, he conjectured that this sequence was log concave. Earlier, Reed in 1968 had conjectured in the graph case that the sequence was unimodal when you're dealing with the chromatic polynomial of a graph. And then Rota and Andrew Heron, one of Dominic's students, conjectured that the sequence was unimodal for matroids. Now, many of you know what's coming next. In 2018, Adeprecito, Ha, and Katz proved Dominic's conjecture. that the coefficients of the characteristic polynomial of a matroid are log concave. And now you remember that first sequence that I talked about, the independence numbers in a matroid? Well, a consequence of this theorem of Adorpacito, Hutt, and Katz is that that sequence of independence numbers is also log concave. And interestingly, that comes from an observation that was made by Matthias Lenz in 2013. But if you go back 30 years before that, Tom Brylowski had observed this back in 1982. And now you'll know that June Ha won the Fields Medal in 2022 for, among other things, proof of the Heron-Rotor-Welsh conjecture. Now, in case you're pining for unimodal conjectures and you think they're all done, one of the conjectures that Dominic had looked at before he made the independence number conjecture was a conjecture of Harper and Rotor. And that conjecture was another sequence that you can associate with a matroid is unimodal. That's the sequence of rank K flats in a matroid. And Junha has made big progress on this, but not settled this conjecture. So that's still open. Let me switch to the Tutt polynomial. Many of you know this story. 4 Cambridge undergraduates who modestly called themselves, what was it? The important members, or the 4 horsemen, Brooks, Smith, Stone, and Tutt, one of whom was not a mathematics undergraduate, looked at the number of spanning trees in a graph, the number of spanning trees in a connected graph, and they proved this deletion contraction formula. The number of spanning trees in the graph G is the sum of the number of spanning trees in the graph G delete E plus the number of spanning trees in the graph G contract E. Tutt wrote, I wondered if complexity or tree number could be characterized by the above identity alone, and decided that it could not. Now, Tutt worked at Bletchley Park during the Second World War, code breaking. He'd been actually a chemistry undergraduate. He returned to Cambridge after the war and wrote a mathematics PhD called An Algebraic Theory of Graphs. And it's an unbelievable document, over 450 pages. And in that, he introduced the Tutt polynomial. He didn't call it the Tutt polynomial, of course, and he wasn't even working for all matroids. He was working for representable matroids, or as he called them, nets. So you take an isomorphism invariant. If you've got M1 and M2 and they're isomorphic, then F evaluated on M1 is the same as F evaluated on M2. And then this isomorphism invariant obeys this deletion contraction recursion that the complexity number obey. What happens if you've got a loop or a co-loop? Well, then you have a multiplicative formula. F of M is F of M delete E, could be F of M contract E because it's a loop or a co-loop, of course. And then this is F of M delete EM minus E. That, of course, is just F evaluated on the element of E. And then suppose that I tell you that I get the value X when I evaluate it on the one element co-loop, Y when I evaluate it on the one element loop. Then the theorem is that this function F is an evaluation of the Tutt polynomial. And this is how it's evaluated. So the key point here is that there's a 2-variable polynomial so that every isomorphism invariant that obeys these conditions is an evaluation of this polynomial. Now, Dominic had what he called a recipe theorem. And that's an extension of this theorem of Tutt. What does it say? Well, same setup as before. You've got a class of matroids closed under isomorphisms, direct sums, and minors, and you've got a function from that class into a field. And it's going to obey a deletion contraction recursion, but the deletion contraction recursion has got multiplicative weights in it, sigma and tau, for some elements of the field. The deletion contraction recursion works if you've got a loop or a co-loop. What if you've got an element that's not a loop, that is a loop or a co-loop? I think I said that wrong, but you know what I'm trying to say. If I've got an element that is a loop or a co-loop, then I obey the same multiplicative recursion that the Tutt polynomial obey. Now, it's not going to surprise you to imagine that what's going to happen here is that this function g is going to have something to do with the Tutt polynomial. And sure enough, it's a weighted version of the Tutt polynomial. So the function g is, you've got a factor of sigma, which is the rank of the dual matroid, tau to the rank of the matroid, and then the Tutt polynomial of the matroid evaluated with these sigma and tau appropriately included. This has lots of applications. Let me just give you one. Take a matroid and delete every element with probability 1 minus p, and do this independently for each element. This is going to give me a random submatroid of my initial matroid. What's the probability that this random submatroid of the initial matroid has the same rank as the original matroid? Well, that's just an evaluation of the Tutt polynomial along with some multiplicative factors. I mentioned that Dominic worked in complexity. This is Dominic giving a lecture in Cambridge, and again, those of you who are familiar with Dominic's work would have seen this diagram many times. Dominic had lots of students who worked in complexity, particularly in the 1980s. That's the part of his work that I know the least about, so I'm not going to say anything more about it, but I think this picture is a memorable one. This picture was taken by Andrew Thomason. I am going to talk about Dominic's work on complexity and the Tutt polynomial, and in particular, his most cited paper. Now, this was a paper with Francois Gégé, Dirk Vertingen, who was one of Dominic's students, and it was entitled On the Computational Complexity of the Jones and Tutt Polynomials. Now, if you're not interested in knot theory, you may not be familiar with the Jones polynomial. Vaughan-Jones, a New Zealand mathematician, introduced this polynomial for knots, and it turns out to be closely related to the Tutt polynomial. And in fact, Vaughan-Jones won a Fields Medal in 1986 for, among other things, introducing this polynomial. Now, if you're going to talk about the computational complexity of something, you have to have some language. Number P is the class of enumeration problems in which the structures being counted are recognizable in polynomial time. So you should think of that as the enumerative analog of NP. A problem is number P complete if any problem in number P is polynomial time reducible to A. And so, for example, counting the number of Hamiltonian paths in a graph is number P complete. And then a problem is number P hard if for any number P complete problem, it's polynomial time reducible to it. Now, immediately, there are some technical issues when you come up with doing computational complexity for matroids. The question is, how is the matroid given to you? because if I just give you a list of the independent sets, the input size is going to be so large that when you measure the, usually you do these computational problems in terms of the size of the input. If the input is too large, then it messes up the results that you get. So Dominic, Francois, and Dirk dealt with what they called succinct classes of matroids, ones that are given to you, say, by a graph or by a matrix, or in the case of transversal matroids, by a bipartite graph. Another thing that if you're not used to thinking about questions of computational complexity, is where are you going to do the calculations? So you just say, those of us who are pure mathematicians say, oh, you just multiply these two numbers. But you can't just multiply two numbers. You've got to make a decision about where you're going to do these calculations. And all the calculations are done in a finite dimensional algebraic extension of the rationals. That includes I, of course, square root of -1, and j, the cube root of 1. Okay. This is the first theorem of Dominic and Francois and Dirk. When you come to evaluate the Tutt polynomial, now you think when you've got the Tutt polynomial of a graph, you've got something useful, and you do have something useful. The problem is that working out a value is really hard. It's number p hard, except when AB is on the hyperbola x minus 1 times y minus 1 equals 1, or when the point AB is one of these 8 special points. And in the exceptional cases, the evaluation can be done in polynomial time. So working out the Tutt polynomial is basically a hard problem, pretty much always. Dirk and Dominic looked at this problem of working out the Tutt polynomial when you take a bipartite planar graph. Surely it's not going to be hard in those cases. Well, the answer is yes, it is. It's number p hard except when AB is on. Now, this time you get two hyperbolas, x minus 1 times y minus 1 equals 1, and x minus 1 times y minus 1 equals 2. And you get only 4 points. Why are there only 4 points? Because 4 of these ones up here turn out to be on the hyperbola x minus 1 times y minus 1 equals 2. So even for bipartite planar graphs, working out the Tutt polynomial at a specific point is generally hard. What did that say about knot theory? Well, the problem of determining the Jones polynomial of an alternating link is number p hard. What's an alternating link? Draw the knot diagram, follow the thing around, the crossing should alternate over, under, over, under. Dirk actually won the prize in Oxford for the best PhD dissertation in his year for this work. And that was certainly cause for celebration. I've mentioned that Dominic organised these two conferences. This is the first British Combinatorial Conference. He edited the proceedings. The third British Combinatorial Conference, he edited the proceedings again, this time with Douglas Woodall. And then he started writing books. In 1976, he wrote his Matroid theory book, which was the first comprehensive treatment of Matroid theory. There were some books that touched on fractions of Matroid theory earlier on, but this was really the first comprehensive treatment. And then with Geoffrey Grimmett, Probability and Introduction, first edition in 1986, second edition in 2014. Now you might wonder why there was no second edition of Dominic's 1976 book. Well, he was approached by Oxford University Press about updating this 1976 book. And he said he didn't want to do it. He recommended that I be asked to do it, and I did. And I had a template there. When I went to write my book, I had his book as a template. And if you look at my book, you will see how closely it's modeled on his book, particularly in the early chapters. He wrote a book on codes and cryptography in '88, a book on complexity, knots, colouring and counting in '93, and a book with John Talbot, Cryptography and Complexity. That was in 2005. Now remember 2005, that was the year that Dominic retired. So he was active right up until he retired and even beyond then. Now, Dominic was a really gifted expositor. He could strip away the technicalities that existed in a subject and very quickly get to an interesting, tractable problem. The problem might not have been able to be solved, but it could be understood and it could be recognised as being interesting. He presented many, many conference talks at the British Combinatorial Conference in 1979 and again in 1997, he was a plenary speaker. And in Vienna in 1980, he was a speaker. He gave 3 invited talks. So this is 3 of us in Vienna in 1980, Dominic and Don Rowe. Don Rowe was a great friend of mine, and he was also Jeff Whittle's PhD advisor. Dominic received an honorary doctorate from the University of Waterloo, Doctor of Mathematics in 2006. And you can see in this picture, I think that he looks a little bit uncomfortable. He was sort of a very self-deprecating man, and that came across a little bit in his convocation address, which I want to quote from. In 1961, I was researching in Bell Labs in New Jersey, and programs were typed on cards, which one carried around in large boxes. Can you see where this is going? My career there nearly came to an abrupt end when I bumped into the chief scientist, who dropped and spilt his large deck of precisely ordered cards. The very first time I met Dominic was in the Porter's Lodge at Merton College. And the very first thing that he did was, I'd addressed him as Dr. Welsh. He straight away said, Dominic. And then he said, come to afternoon tea. And so I went to afternoon tea with Dominic and Bridget. And I thought, you know, I'm getting special treatment. But no, I wasn't getting special treatment. This was a treatment that all of Dominic's students got. This was the way that he treated everybody. There was a retirement conference in 2005, attended by a number of Dominic's former students, and the proceedings were edited by Geoffrey Grimmett and Colin McDermott, 2 of Dominic's students, a tribute to Dominic Welsh, which appeared in 2007. I think it's clear to you by now that I have the greatest admiration for Dominic. So I can't really add any more to my strong feelings about him. But what I'd like to do is I'd like to show you that my feelings are representative of those of all who interacted with him. And one of the wonderful features of Geoffrey Grimmett's obituary of Dominic is that he quotes from a number of former students of Dominic. And so let me repeat some of these quotes. First, from Andrew Wiles. He talked about his time as an undergraduate at Merton. Dominic's presence was certainly the best part of it, and I will always cherish his friendship and kindness then and afterwards. Another one of Dominic's students, David Sturziker, became Professor of Mathematical Statistics at Oxford. Dominic's pupils generally found him to be one of the most engaging and entertaining of all their lecturers. He conveyed the impression that he was enjoying it and found it fun to be talking to us. Colin McDiarmid became a Professor of Mathematical Statistics at Oxford. He talked about, before I came to Oxford, I'd certainly enjoyed mathematics, but with Dominic as supervisor, the game changed. Mathematics became very exciting with a playful side, something to share. He was a great storyteller, always with a smile and a laugh. Now, there are some other comments that I want to give. These are taken from the tribute page of Dominic, and they come from former students of his. First of all, Priel Marino. What the mathematicians who knew Dominic are going to miss most is his ability to craft nice, easy to state, deep problems that always create an interest in those listening. Another of Dominic's students, Andrew Goodall. Communication by glint of eye and startling movement of eyebrows, his infectious good spirits, the conjecturer, pick a memory, any memory, and Dominic gives you something to smile about. Now, there's another tribute on the web page that is written by someone who was obviously Dominic's undergraduate student. And I want to present it because it's I'll let you read it. Dominic was a wonderful tutor who changed the course of my life by seeing that I was unhappy and offering me another path after graduation. I've never forgotten his kindness and the time he took to help me when I barely knew myself that I needed help. In 2010, Dominic's 1976 book was reprinted by Dover. I've headed this title Generosity of Spirit because Dominic actually apologised to me because he was worried that this reprint of his book would hurt the sales of my book. When we were in Verena, I asked if I could borrow Dominic's problem book, and he just gave it to me. You know how valuable having a collection of problems are. He just gave it to me. So I like this photograph. Again, it's another one of mine. I think it's a beautiful photograph of Dominic. Solving conjectures, you will see, is going to be the way that I close this talk. So, solving conjectures. In 1995, my former student, James Reed, invited Dominic to be the Dalrymple lecturer at the University of Mississippi. And I was charged with introducing Dominic. Now, I didn't want to do an ordinary introduction. I wanted to do something unusual. And growing up as an Australian, what came to mind but waltzing Matilda, of course. Now, waltzing Matilda, for those of you who don't know, was for many years and probably still is Australia's unofficial national anthem. So it's got verse, chorus, verse, chorus, verse, chorus. There are some people who feature in this story that I need to tell you about. Paul Seymour. Well, Paul Seymour was, as you all know, and still is, an extraordinary problem solver. Dominic called him Wonder Boy because he could do anything. One of Dominic's conjectures he called the shameful conjecture. It was shameful because it was obviously true, but no one could prove it. And what was this conjecture? It was that a certain parameter was greater than E. What's E? 2.71828. What could Seymour prove? Not 2.71828, but only 2.71825. So even Seymour couldn't do it. It was subsequently done by Fengming Dong. So I'm going to close with this homage to Dominic and to A.B. Banjo Patterson, Waltzing Matilda, because I think it captures the joy that all of us felt of doing mathematics with Dominic. And I'm not going to try and read it. So let me go back to this picture of Dominic. I've lost it. There it is. Let me close with that. Thank you very much.
Thanks, James. Does anybody have any comments or questions they would like to add? If not, I think we should all unmute ourselves and give James a round of applause. Thanks very much, James, for a beautiful talk.
Thank you, Jim.
Thanks, James.
I think maybe we could stop the recording and then just have a chat. Yeah, that was really nice. Thanks very much.
Well, you could see that it was a bit too much for me at times, but we really were very great friends.
Thank you, James. And it was lovely seeing all those names and hearing the maths again. Thank you very much.
Thanks, Bridget.
I was wanting to know the answer to your percolation question from the start of the talk.
I think the answer is a half, and I think that's the thing that Harry Kersten proved. And actually, it's interesting because when I was a student, there were a bunch of physicists that sort of had an ad hoc, experimental way of doing the thing. They thought, okay, this is how you prove a theorem. And so Dominic invited one of them at least to come to give a talk in the seminar in Oxford, but they couldn't do it. They had experimental results, but they couldn't do it. And I think it was Harry Kersten, the famous Cornell probabilist, who did it. And it was done in the early 1980s. And you can do the thing not just on a square grid, but you can do it on a triangular grid and a hexagonal grid. I don't know what the answers are for those.
So there are a list of his conjectures that are still alive out there now? Has anybody collected his conjectures? He made a lot of conjectures.
He made a lot of conjectures, yes. And I sort of thought that, these conjectures were really serious. And it took me a long time to realize that a lot of them were just ways of entrapping me and getting me to do more work. Because you'd have a conversation with him, you'd work, and then he'd say, I reckon this is true, this is a conjecture. And why don't you go away? And of course, that was a spur. You got this conjecture, you want to prove your advisor is, you probably want to prove that he's wrong. And so, you know, that was a great source of stimulus. And he wanted to draw people in to working in his subject. And what's a better way of doing that but tossing out lots of conjectures?
I remember I
And
was having a discussion with him once where he posed some ideas and put forward a conjecture in one way, and then it looked really plausible, and then he said some other ideas and posed another conjecture, and that looked really plausible, and he explained why those two things were opposite to each other.
Yeah, well, I mean, that's the thing. And he was just marvelous at really drawing people into mathematics. And I mean, one of the things I like about this picture is that it really captures just the joy of the man, and also just, you know, it was really wonderful to interact with him.
Yep. Does anyone else have any
Honestly,
reminiscences they want to add?
I'm really proud of this.
Yeah, this is good.
I changed the end a little bit because, you know, when I originally did it in '85, Dominic was obviously alive, but, you know, I changed the end a little bit. But and you remember when I did this talk on Tut, I finished with his Blanche Descartes' poem. But I knew I wouldn't get through this, so that's why I just left it for you to read. And it's Anzac Day in Australia, so what better day to do something like waltzing?
I'd missed that fact.
What do you mean you'd missed the fact that it's Anzac Day?
I hadn't noticed.
You're a. I'm
I was
just
going
going
to get my
write
citizenship
down.
revoked.
Exactly, that's what I was thinking. I'm just penning the note now. Please. Yeah, indeed.
Not only that, but I'd actually been told already on Sunday, and I'd forgotten.
Oh, well, that's part of being 53, I'm afraid. Wait till you get to be 70. When you get to be 71, it's even worse.
Well, James, it's Simon here. I just want to say thank you so much. Really, and everybody for joining as well, and who contributed. It was really a wonderful thing to watch. Thank you.
Thank you,
And
Simon.
really
I'm
well.
sorry. I'm sorry I broke up at a few points, but it was
No.
it was just very hard to do.
No, it was excellent. Thank you. Thanks everyone for hosting.
Thank you, Simon.
Maybe I'll go ahead and stop the recording now.